Hi, in this part of the video we're going to be looking at the integration aspects of variable acceleration. So just a recap of what I was talking about in previous videos. We have a velocity time graph on the left here, and that's what we were seeing in constant acceleration. So if we were trying to find the total distance travelled or displacement, we would be looking at working out the area underneath the graph, and we could use the area for a trapezium or split it up into two triangles and a rectangle and find the area from there. We're going to be using functions still, curves in this chapter, so more likely we will be finding the area underneath a curve for this velocity time graph on the right, and it might be that we're going to have to do it between particular limits. So t can be 0 there, and then 1, 2, 3, 4, 5, 6, 7, 8. T will be 8 there, and we'll have to integrate between the two limits. So just to recap, that we can integrate to find velocity if we've got acceleration. We can integrate to find displacement if we've got velocity. So we can integrate to move between displacement, velocity and acceleration. So if we go straight into an example, a particle is moving along the x-axis. At time t is 0, the particle is at the point where x is 5. So I'm just going to highlight or underline that. Time t is 0, the particle is at the point where x is 5. The velocity of the particle at time t seconds, it's given as our restriction, t has to be greater than or equal to 0. This is our velocity. Find part A, an expression for the displacement of the particle from O at time t seconds. So we're finding displacement. So I'm going to integrate the velocity to find the displacement. So I'm going to say x is equal to the integral of v, and then with respect to t. So I'm integrating v with respect to t. Now you don't have to write this step, you could write this step first, and I will put a bracket around it. So that means when I integrate then, and I'm presuming you know how to integrate this stage, I will get that with a plus c. So it wants an expression for the displacement. I will need to work out what this value of c is here. And they've given me some information in order to find that c value. If you think back to integration, usually you were given a point to find it, an x value, a y value. We're working in terms of x and t, so it's what I highlighted right at the top here. So at time t is 0, x is 5. So I'll put that in. When t is 0, x is 5. So I will change those. So therefore c must be 5, because you can see those will go to 0, and then you'll be left with c equals 5. So therefore an expression for the displacement I will just write now with a plus 5. So you can see I did have a diagram here of the velocity time graph, and I will have integrated to find the displacement. Part B, the distance of the particle from its starting point when t equals 6. Well, I've got an equation for the distance or displacement, and I want to work out what the distance is when t is 6. I'm going to say when t is 6, substitute it in, I will get 108 minus 72, add 5, x is 41. Now we need to be very, very, very careful here. It says the distance of the particle from its starting point when t is 6. Now let's just double check its starting point. At time t equals 0, that's its starting point. Well, the particle was already at x equals 5. So from O, the expression for the displacement we found in A, that was from O, but its starting point was already 5 meters from O. So if I just draw a little diagram, this could be O. Then its starting point at t equals 0 was 5 meters. And then we've just calculated that when t is 6, we've got 41 meters. So actually the distance of the particle from its starting point is going to be that distance there. Okay, so I will say, I'll do it underneath, therefore distance from the starting point equals those two taken away, which is 36 meters. So the velocity time graph wasn't really needed in this question. I did go ahead and draw the displacement time graph just to show you what we got. Remember, we are integrating now, so we've gone from a quadratic to a cubic, and if it's talking about the distance travelled, well, we could have looked at where t is 0. You can see at t is 0, it should be x, not s. X is 5, so that's why c was 5, the intercept. And then we were looking at when t is 6, so 2, 4, 6, this line up here. When t is 6, that point is 41. Next example, a particle travels in a straight line. After t seconds, its velocity, v meters per second, is given by this. There's our restriction. Find the distance travelled by the particle in the 3rd second of its motion. So if I just think about what this means, I'm looking at distance travelled, but what does 3rd second of its motion mean? Well, say I am at time t is 0, then I'm at 1 second, 2 second, 3 second, 4 second, 5 second, and so on. I want to know what the 3rd second of its motion is. Well, this bit here must be the 1st second. So going from 0 seconds to 1 second, that's its 1st second. This one here is its 2nd second of motion. Okay, going from 1 second all the way to 2 seconds. So the 3rd second of its motion is actually here. Yeah, that's the 3rd second of its motion. So I'm going to be between 2 seconds and 3 seconds. Now I could draw a quick sketch on this one. I'm just going to show how I would sketch from scratch. So it's velocity and time. And I've got 5 minus 3t squared. So if I was thinking about solving that, I'll have 3t squared equals 5, t squared equals 5 over 3, and then t is plus or minus root 5 over 3. Now it's going to look fairly symmetrical, well, pretty symmetrical on this one. So I'm only looking at the positive t values, so it's going to be an upside down parabola, so something like that. This will be root 15 over 3, sorry, not root 15 over 3. It can be root 15 over 3 if you rationalise the whole of root 5 over 3. That's how the calculator writes it if you solve it. But if I just write root 5 over 3 there, that's roughly 1.29. Okay, so in its third second of motion, it's actually going to be part of the graph that's underneath here. So if I carry on it down like a quadratic, the rest would come down here. If this is 1.29, 2 could be like there, and 3 could be like there. So if I carry on that down a little bit, I'm looking at the area of that part. So from the t-axis to the curve here. Now hopefully you've spotted what's going to happen. When I integrate between these two values, I should get a negative answer because the area I'm interested in is underneath the t-axis. So let's have a see if that works. If I just move up slightly, I'm going to be using v equals 5 minus 3t squared. And I need to differentiate that because it's integrate that because it's talking about distance. So I will use S for distance. It's not giving me any letter, so I'm using S. So that will be the integral of 5 minus 3t squared and then dt. And I'm going to put limits on here. So I'm going between the limits of 2 and 3, the largest limit on the top, the smallest limit on the bottom. And if you remember, you've got your square brackets when you've integrated. And 3, 2 there. So I'm going to substitute in 3. And take off 2 substituted. Now, if you calculate that, you're going to get negative 14. And you might want to make a note of that. That's just because it's below the t-axis or the horizontal axis. So I was anticipating a negative value. So I don't want a negative answer because it's distance travelled. So this is just showing me with a negative value that the particle is 14 meters away in the opposite direction to what's positive. So I just want the distance as a whole. Well, it's travelled 14 meters, this particle. So the distance travelled equals 14 meters. I'm going to go on to another example. Example 3. A particle travels in a straight line such that its acceleration at time t seconds is that. So we've got acceleration, that's our equation. The velocity of p, the particle, at time t seconds is v meters per second. So that's just giving you all the variables, it's giving you the units. It's also given us this, so when t is 0 at the start, its starting point, the velocity equals 4. We've got to find v in terms of t in part A, so that's the velocity. And if I've got the acceleration, I'm going to be integrating the acceleration. So I'll just write that down. A is t minus 3. So to get v, I'm going to integrate A with respect to t. Again, you don't have to do this step, you could jump to this next step. When I integrate that, I get this with a plus c. And they've given us a point here, like you would with normal integration. So when t is 0, v is 4, so if I sub that in, I can see that c is 4. And some students will be able to jump straight to there because this is the y-intercept if you think about it. When t is 0, v is 4, so c must be 4 being the y-intercept. So you can jump to what the value is there. So that is v in terms of t. Right, b, the values of t when p is instantaneously at rest. So I've got the actual graph for the velocity now. So you can see there that it's a quadratic, it's going through 4 on the vertical axis, and it wants the values, so there's going to be 2, the values of t when p is instantaneously at rest. So I know that's when v is 0. So I'm looking on the graph, I should be able to see there that I should be getting t is 2 and t is 4. So I'm going to be solving the equation. You could multiply through by 2 if you like here, or just jump and use your calculator. I'm going to get t is 2 and t is 4 from using the calculator. So as you can see, that's what I was expecting. Right, part C, the distance between the 2 points at which P is instantaneously at rest. Distance, now the 2 points that it's talking about are 2 and 4, the ones we've just worked out when it's instantaneously at rest. So I'm going to be integrating to find the distance. So I'll have to integrate the velocity, and I'm going to be using the limits of 2 and 4. So S, I'm going to call the distance, is equal to the integral between 4 and 2 of this with respect to t, square brackets when I'm integrating, and if I substitute in 4, and take away me substituting in 2, And then when I work that out, I should get 8 over 3 for the first bit minus 10 over 3 for the second bit, and that will leave me with minus 2/3 meters. So again, it must have been the area under, and as you can see it was. We were integrating this particular area here, so that's why we've got a negative. And because it's distance, therefore distance is going to be 2/3 of meters. You can write that as a decimal if you want, but obviously we know what 2/3 is. I'm just leaving it as it is. Just a reminder that you can double check your definite integration on your calculator. There is a button that you can use, and you can double check that you get the correct answer. Alright, so let's go and see what practice you can be doing. So 11D is some practice, and we're just going to have a look at a challenge question now. So the motion of a robotic arm along a straight track is modelled using these equations. So you've got the velocity here and the velocity here. You've got the restrictions, so this one's between 0 and k inclusive. This one's between k and 10 inclusive. The diagram shows a sketch of the velocity time graph of the motion of the arm, and we've got to work out the total distance travelled by the robotic arm. And if you remember, the total distance travelled, or anything to do with distance when we've got a velocity time graph, is the area. Now, why have we got two equations? Well, it's because we've got this weird looking shape for the velocity time graph. So actually this part is the first equation, and then the second part is the second equation. So actually I know that this one is going between 0 and that point there. That must be k. And the other one is going from k to 10, all for t. So I'll have to split this one up. When I find out what k is, I can find the area underneath the curve, and I'll call that A. And then I can find the area under the second curve, and I'll call that B. But first I need to know what this limit is going to be, what k is going to be. Well, they both share the same point. They both share this point, so whatever that point is there. So if I can solve simultaneously, I could make them equal to each other because they're both equal to B, and then solve. I'm only interested in the t value, I'm not interested in the v value. So I'm going to partially solve simultaneously. So I will do the steps. I'm going to find k first, and as I'd said, we can make them equal to each other. Now I'm just collecting everything together. You can multiply through here. You might want to multiply through by 12 so you get rid of all the denominators at once. But I am just going to work with the fractions for now. Here again at this stage you could multiply through by 12 and get whole terms, but I've just used my calculator from this point. So t is 4 and t is equal to minus 24 over 7. Now I'm going to reject this one because t has to be greater than or equal to 0. It does say that in the restriction. So therefore, if that is 4, then that point, k must be 4. Okay. So now I've got this, which is 4. I can now integrate twice to find two separate areas and then add them together. So I'm going to look at area A first, and I'm going to do definite integration with the limits 4 and 0, and I could call that S1 if I wanted to, and it's going to be, now I'm writing t squared over 2 as a half t squared, it's just easier to integrate, so I will get this between the limits of 4 and 0. I'm going to apply those limits. Remember, when you sub in 0 at any point, it's just going to be 0 because you always have terms in terms of t. And when I do that, I get 56 over 3 meters. Now, both these areas should be positive because they're both above the t-axis, and remember, you can check these on your calculator. I'm going to do the second distance now, finding the second distance, which is part B area. So I'll call that S2, and I'm going between the limits of 10 and 4. And if I just scroll up a moment, I'm using the 10 plus t over 3 minus t squared over 12, and I'm just going to write that with fractions instead, a little bit easier to work with, like that. Integrate 10 10 will become a 10t, then I'll get a 6t squared minus 1 over 36t cubed, and then between 10 and 4. So I'm not going to show me substituting that in. You can do the substituting in step. I'm just going to jump straight to my calculator. So I'm using that button that I'm talking about, and I'm putting in the limits from 10 and 4, and I'm typing in the part that I've integrated. And I'm getting 48 meters. Okay, so when I integrate 10 plus a third t minus a 12t squared, between the limits of 10 and 4 I get 48, so just double check that. And then therefore the total distance is going to be 56 over 3 plus 48, which is 200 over 3 meters. Alright, so this is where I'm going to leave this video.